Welcome to The Explainer. You know that feeling when you search for something and the answer pops up instantly? Well, today we're going to pull back the curtain on one of the secrets to that speed, a really cool data structure called the binary search tree.
All right, let's kick things off with a problem that's like everywhere in our digital lives, even if we don't see it. How do you find one tiny piece of information, a needle in a digital haystack, and get it back, like right now?
Seriously, have you ever stopped to wonder about that? How does your favorite shopping app find that one specific product out of millions in a split second? Or how does your phone pull up a single contact from your address book without making you wait? It's not magic, but it's close. Okay, so here's the deal. The slow way, the dumb way really, would be to check every single item one by one. You know, like trying to find a word in the dictionary by starting at A and reading every single page. No one does that, right? Instead, you use a much, much smarter way. You jump, you divide and conquer. And that is the whole secret behind a binary search tree. So this super smart structure, the binary search tree, or BST for short, has all this power, all this speed. And it all comes down to one simple rule. I mean, it's so elegant, it's almost beautiful. All right, you ready? Here's the rule. For any piece of data, we call it a node. Everything to its left has to be smaller, and everything to its right has to be bigger. That's it. Seriously, smaller things go left, bigger things go right. That one little rule is the key to everything. And this simple logic, less than, go left, greater than, go right, is the engine that drives the whole thing. Think of it like a series of forks in the road. At every single stop, you make one simple decision, and in doing so, you get to completely ignore a huge chunk, like half, of the data you don't need to look at. It's incredibly efficient. Okay, so now that we know the rule, let's put this thing to work. We're going to see how this one simple idea makes the three most important jobs, searching, inserting, and deleting data, so ridiculously fast. All right, first up, let's go hunting. This is what we do most often, right? Searching for stuff. Let's say we need to find the number 66 in this tree. So, where do we start? Always at the top, at the root node. In this case, that's 58. First question. Is our target, 66, bigger or smaller than 58? Well, it's bigger. So what does the rule say? Greater than, go right. Easy. Okay, step 2, we're now at node 73. We ask the same question again. Is 66 bigger or smaller than 73? This time, it's smaller. So we go left. And just think about what just happened. We instantly ignored everything to the right of 73, and we already ignored everything to the left of our starting point. We're cutting down the search area like crazy. And boom, step 3, we land right on 66. We found it. Match. Look at that. In just 3 little hops, we navigated through all this data and found exactly what we were looking for. So this table just shows you the path we took. See? Just a few simple comparisons, but each one took us on a direct path, allowing us to just completely throw away massive parts of the tree we didn't need. No wasted time. So what if you want to add something new? Well, it's pretty much the same exact logic. You basically pretend you're searching for the number you want to add. You follow the left for less, right for more rule until you hit a dead end, an empty spot. And once you find that spot, you just plug your new node right in. Simple as that. Okay, now for removing data. This is the trickiest operation of the bunch. You can't just yank a node out of the middle of the tree because you'll break that one sacred rule we've been talking about. So to do it right, we have to think about 3 different situations. All right, the first couple of cases are pretty straightforward. If the node you're deleting is a leaf, meaning it has no kids, you just clip it off, done. If it has only one child, its kid just steps up and takes its place. The family tree stays in order, no problem. But what if the node has 2 children? Now things get interesting. You gotta find a replacement. The answer is to find what's called its in-order successor, which is just a fancy way of saying the very next biggest number in the entire tree. You find that number, promote it to the empty spot, and voila, the tree's ordering rule is saved. So, this all sounds amazing, right? Super fast, super elegant. But there's a catch. Of course there's a catch. All this BST magic, it only works if the tree has a nice, healthy shape. And this is fascinating. The shape of the tree depends entirely on the order you put stuff in. If you throw numbers in randomly, you get this beautiful, bushy, balanced tree on the left. Super efficient. But if you insert numbers that are already in order, you get this disaster on the right. It's basically just a glorified list, and all that speed is gone. And the difference in performance is just wow. The balance tree on the left is what we call O log n. All that really means is that it scales like a dream. You can double the data and it only adds like one extra step to your search. But the unbalanced tree, that's ON. That means if you double the data, you double the search time. It's just as slow as checking every single item one by one. The magic is completely gone.
Okay, so let's tie this all together. Why does any of this matter? What's the big payoff? Well, because this one little idea, this one data structure, is hiding under the hood of so much of the tech you use every single day. I'm serious, this isn't just some abstract theory. This is the secret sauce in database indexing. It's how your computer's file system works. It's behind autocomplete when you're typing. It's in dictionary lookups. It is everywhere. Oh, and get this for a cool bonus feature. Because of that strict, less on the left, more on the right rule, you can walk through the tree in a special way. It's called an in-order traversal, and it'll just hand you all the data back, perfectly sorted. It's like getting a free sorting machine built right in. Isn't that just incredible? This beautifully simple idea, born back in the 1960s, is still one of the fundamental pillars organizing our digital world today. It really makes you wonder, doesn't it? What elegant ideas being dreamed up right now are going to become the invisible engines that shape our future?